that, but from now on we'll be recording. That little red circle there with the number counting down, that indicates we're recording. If you ever not see that, tell me you're not recording. Okay. So the first law of motion, they came up with these 3 laws of motion and many other laws. This is basically became the foundation of physics, okay? But he also came up with the law of gravitation. Never had one before. He came up with much research into light that we had never had before. And in the process of doing this, he had to develop a whole new branch of mathematics called calculus in order to describe all this stuff. An incredible individual with incredible outreach in just about every area he touched. Okay? And his first law of motion is called the law of inertia, and we talked about that, but I did not give the definition of it. That's on page 124 if you do have a text, about the middle of the page, just under the law of inertia there. And here is the, let me get my pen set up. Okay, inertia. Now, does anyone, I think I asked this question before, what does inertia mean to you? How about the first 5 letters of inertia? What does that mean? Say again? Not moving, okay? Inert, just hanging there, doing nothing, inert, okay? Guy in front of the TV on a football Sunday, okay? Not doing a thing, okay? So that's half of what inertia is, but that's where it got its name. Inertia is the property. These are for those who don't have a book. Now, do all of you have books? No, okay. I thought there were a few without, and some people are not here, so just in case. Inertia is the property, okay, of a body that, let's see, of resisting, that causes it to either remain at rest, if that was its initial state, being at rest, like the guy on the couch, okay? If it is at rest, or to continue moving, my writing is awful, and I abbreviate like crazy, with a constant velocity, okay? Now, unless an unbalanced force acts on it. Okay, that's what inertia is. The property of a body to maintain its state of motion. If it is at rest, it tends to stay at rest. If it is moving, it continues to move it at that same velocity. Now remember, velocity is a vector quantity which has 2 features. Magnitude, how fast is it going, and direction, what direction is it going. So a constant velocity is going to maintain its speed, but also maintain its direction, okay? Unless there is an unbalanced force acting on it. And we talked about bowling balls and things like that last time, I believe. That's what inertia is. Some examples of this that are pretty common, I can't remember if we did these last time or not, I don't recall doing them. Have you ever been on a bus and had to stand on the bus, or a train, or something like that, had to stand because all the seats were taken, hanging onto a pole or a handle or something like that, and suddenly the vehicle took off suddenly? What did you do? You fell back. No, you didn't. You were trying to maintain your position. It was that the vehicle was moving out from under you, okay? Or you were standing there and it came to an abrupt stop, and what did you do? You felt like you fell forward, but no, you didn't. You were trying to maintain your state of motion. You were going along at a good certain speed, and suddenly it stopped. You were trying to maintain. That was your inertia. Or hanging on there, and suddenly it made a sharp right or left turn. What did you feel like you were doing? Thrown against the side, one way or another, in the opposite direction. No, you were trying to maintain your state of motion. That was your inertia. Trying to maintain the state of motion. A couple of vehicles ago, I had a little Ford, Ranger pickup, okay? And I can remember my lawnmower, I started noticing when I poured gas in, I started getting gas out, found out there was a leak in the gas hose. So I had to haul it off to a place to get it worked on. Put it on the back of the truck. I tried to chock the wheels so it wouldn't be moving around. They didn't work more than a block or two. And every time I would take off, boom, I'd hear it hit the back. Or when I'd stop, boom, it hit the bed, the cab. Or turn one way or another, I'd hear it slide one way or another into the wall. It was trying to maintain its inertia, its state of inertia, even though I was driving in ways that made it hit the sides. It wasn't. Now, sometimes you hear people talk about this is centrifugal force pushing it that way. No, it's not. It's the inertia of the body trying to maintain its current state. That's what it is. Okay? Maybe way more on inertia than you ever wanted to hear. But let's get out of this one and go to this one. Okay, one more slide, and we'll go from current slide. All right, here's a guy pushing hard on some sort of a crate or box or something on fairly rough-looking road. Looks like he's straining away. Why? Well, the box was at rest, and it's trying to remain at rest. But he's trying to get it to go that way. So he's having to apply an unbalanced force. Now, if the friction between the road or the driveway or whatever this is and the box is so great that his push on it is not moving it any, it's maintaining its state of inertia. It's at rest. It's not moving. So therefore, there is no unbalanced force because his push is being exactly balanced by the frictional force between the box and the road. So there is no unbalanced force. But if he does manage to get it moving and make it change its inertia, then his force has exceeded this one. So now you have an unbalanced force. That's an illustration of inertia. This picture indicates the box is winning. Its inertia, the friction that it has is equaling his push, so it's not changing its motion. Okay. And as I said before, these are lousy the PowerPoints are okay, but that next PowerPoint that shows up is 6 pages away, okay? Everything in between, I go back to the other slide, okay? And rather than try to draw that, now, there is a problem with this approach to it. People at home will not be able to see what I'm holding up here. But here's another example of that. If a car is moving down the road, okay, there are several forces acting on it. The wheels are pushing on the road, okay, and that's friction. If you didn't have friction, they'd be spinning, okay, like on ice or something like that. If the car is moving down the road, you have air resistance resisting, you have the friction of the road resisting, and you have to be adding an unbalanced force to make the car move, okay? And that's what you do when you step on the gas. Now, If the car is on ice, then you have no friction there. And if you are moving, you continue moving because you have no way to stop it, because there's no way to have an unbalanced force to change its inertia. Okay. I give this example sometime. Well, we'll come up with that one later, okay, when we do a little bit more definitions, okay? There are a couple of inertia tricks. I don't know if you've seen these before, but if you were to set, in fact, I think I'll do one. Okay. What is going to happen if I place this pen on the piece of paper and jerk the piece of paper out from under it? What's the pen going to do? It's what? Begin rolling. Let's see. It stayed pretty much right where it was. Why? It's inertia. There was very little friction between it and the plate. It moved just a little bit at the very beginning because there was a little bit of friction, but basically its inertia kept it right there without moving. That's an example of inertia. Now, I've seen people do this with plates and a tablecloth. I sure don't want to do it to my wife's china, and do that in case it doesn't work, but you've seen people do that, and be sure the tablecloth doesn't have a lot of texture to it, doesn't have big seams in it, otherwise you're going to be pulling the plates and stuff onto the floor, and that will do. But that's an example of inertia. Okay? Now, inertia leads to another quantity, and it's closely related to this other quantity, and this quantity is called mass. Now, every time I change slides, I have to go back and change my pen color. It always reverts to red when everybody uses black. Some objects, more than others, tend to resist to changes of motion. Would you say that's true? Okay. What if I threw you a ping pong ball? What are you going to have to do to change its motion? Is it going to take a lot of energy to stop it? No. Okay. What if I threw you a bowling ball? That's going to be a lot more to change its motion, to stop it, right? So yeah, there is a difference there. Much easier to push a small automobile than to push a large truck. Yes, okay, into motion. Here is the difference there. The concept of mass. Mass is, believe it or not, a measure of the inertia of a body. Okay. Now, most of the time we think of mass as how much of an object there is. I have way too much mass. I should lose a little bit of it, but haven't been able to lately, okay? And we think of that, but really mass is a measure of the inertia of a body, okay? That transfer truck has a whole lot more mass than that little Volkswagen Beetle, okay? So if they were to ever collide, truck wins. Beetle loses big time, okay? Because it has so much more inertia, okay? The larger body in mass has a greater resistance to change of motion than the smaller ones. That's why it's not a good idea to pull over suddenly in front of a big truck. You might be able to do that quickly. He will not be able to, okay? Because his mass is so big, it's going to be hard for him to adjust. I say him, but it could be a her. Now, I was in the Navy, and if you can imagine when you're driving a ship at sea, a little bitty boat of some nature, it's real easy to change its direction. A great big old battleship is going to take a long time to change its direction. It has that much more mass. The inertia is much harder to change. Okay, that finishes 5.2. Let's move to 5.1. Let's move on to 5.2. The second law of motion, the first law of motion was the law of inertia. Basically, an object maintains its state of motion unless it's acted on by an unbalanced force. Okay? The second law is related to that pretty clearly. Okay? The second law is the law of acceleration. First law, law of inertia. Second law, law of acceleration. And here's what it is. It's Newton's second law. Law of acceleration. Okay. It relates an applied force to the mass and acceleration of an object, and here's how it states. The total force acting on a body is equal to the mass of the body, that's a measure of inertia, how much of the body there is, okay, times its acceleration. Now this is a real simple question, so don't think it's anything fancy about it. What mathematical operation are we talking about when we say times? Multiplication, of course. So here's the formula that states Newton's second law most succinctly. Force equal mass times acceleration. Now, there are many kinds of forces, okay? This is what we call the net force. This book calls the total force. That means the vector sum of all the forces acting on a body is equal to the mass of the body times its acceleration. All right. So putting it sort of in context of the last one. An object maintains its state of motion unless it's acted on by an unbalanced force. What the second law says, if there is an unbalanced force acting on a body, then it changes its motion. In other words, it accelerates it. Now, I believe I started this process last time. Can't remember if we ran out of time or I just stopped doing it. But let's think back. In physics, we deal with quantities. One quantity is distance. I move from there to here. Okay? Now, distance, the other quantity involved there that you probably didn't see was time. It took me a certain amount of time to go from here to there. And the time rate of change of my distance, that's equal to speed. Or, and we mentioned this one before too, I'm pretty sure, not only did I go from here to there and move that distance, I also moved in that direction. The time rate of change of, and that's called, by the way, distance with direction is called displacement. Displacement. The time rate of change of displacement is called velocity. Now, when I say time rate of change, when you hear rate, think division. Okay? So speed is equal to distance over time, time rate of change of distance. Velocity is equal to displacement over time. Now, how I distinguish between distance and displacement, I make displacement a vector because it has direction. So that makes velocity a vector. Speed is not a vector, it's a scalar. Okay? Now, so the time rate of change of your displacement. Now that includes how fast you're going, but it also includes what direction you're going. If you change direction, you're changing your velocity. Okay? If you change your speed, you're changing your velocity. Both of those are changes direction, or a change of velocity. Speed, however, is just distance over time. It doesn't matter what direction you're going. So there's no direction associated with speed. Okay. Now, anyone know what the time rate of change of velocity is? Okay, let's think about it. In your car, when you're wanting to change speeds, what do? You do what? Press the gas. What's another name for that pedal? The accelerator. You're accelerating. So acceleration, also a vector quantity, is the time rate of change of velocity. Okay? Now, I keep saying change of. In every one of these, I really should use another symbol here, and that's delta. Delta means difference. What operation are we dealing with the difference? Subtraction. Subtraction, okay? Okay, so this means, and here's what delta means. V final, always the final, minus V initial. That's what the delta means. You start at initial, subtract that from the final. That's how much you changed your velocity. Okay? Your delta time is the time final minus time initial. Now notice time is not a vector quantity. It only has a magnitude. It doesn't have a direction with it. Now I know Back to the Future made you think it had direction with it. That really doesn't. Time is just a scalar quantity. Okay? So this is what we mean by acceleration. Time rate of change of velocity. Okay? So if we go back to this, the total force acting on the body is equal to its mass times its acceleration. Okay. Now, let's go back to that guy pushing on the box. Remember? Pushing. He was straining on that box, but it wasn't going. What was the total force on the box? 0. Because it wasn't changing its acceleration. It wasn't changing its velocity. It was not accelerating. He was pushing with a force, but guess what? There was an equal and opposite force of the friction between the road and the box that was keeping it from moving. So there was no net force or total force on it. He was pushing this way, friction was pushing that way. The total force on the box was 0. You could tell that it wasn't accelerating. Okay? Now, if it was moving, if it did start accelerating, change its motion, then you know his force overpowered the force of the friction and it started moving. So then there was a net force because it was changing its acceleration from 0 to some positive value. So that little pedal on the floor, we call that the accelerator. Is that the only accelerator your car has? What other acceleration could it have? Accelerator could it have? What's the next pedal do it? What does the brake do? It changes its velocity, doesn't it? It goes from moving fast to stopping, okay? Or slowing down anyway. So that's an accelerator. It's a negative acceleration, but that's also an accelerator. Is there any other device on your car that changes the car's velocity? The steering wheel, because now you're changing the direction. So all three of those are accelerators. We only call the gas pedal the accelerator, but actually the brake and the steering wheel are also accelerators because they change the velocity, which means they accelerate the vehicle. Okay? So the total force on a body, total force, not just the force that he's pushing with, the total force, that counts the others, times is equal to the mass of the body times its acceleration. If it's not accelerating, there is no net force or total force on the body. No matter how much you're pushing or pulling on it. If it's not accelerating, there's no net force. So let's take a big old jet airliner, okay, full of people, flying at a 500 miles per hour. It's a nice level flight. What's the net force on that plane? Also straight line. What's the net force on the plane? Say again? It's hard to say, isn't it? No, it is. What did you say? Oh, okay. Here's you have a large jet airliner filled with people flying at constant elevation, straight direction, 500 miles per hour. Steady speed. Okay, let me get your name, please. Taylor? Oh, Kayla. Got it. This is your first time here, right? Okay. Let me take a time out then. Hang on to your airplane now. It's going to hang in there for a while. Let me go over what we've done so far and how to catch up. Okay? Out there on Blackboard, are you familiar with Blackboard? Okay. Out there on Blackboard, if you go to this class in Blackboard, the home page, you know there's a series of tabs over in the left-hand side. Okay? And they go in groups, sometimes 4, 5, 6, 8, whatever number per group. In the very first group, just about the middle of that first group, there's a tab that says Syllabus and Book Information. You go there, you'll see the syllabus for this course. Okay? And most of what you need to know is there if you want to just read it. Okay? Just below that is another tab that says Instructor Information and Office Hours or something like that. Okay, if you go there, you'll see my locator card. That's when I'm on campus, off campus, which campus I'm on, when I'm in class, out of class, at lunch, whatever. Just about everything you need to know about where I am during the week is there. Now, let me tell you this. Monday through Thursday, except for Wednesday evening when I'm over here, I'm usually on the Bessemer campus, and it lists my office and everything over there. I leave the Bessemer campus between 3:45 and 4, usually right around 4, to get over here to teach this class from 4:30 to 6:30. And then I'm here until I shut everything down and get a chance to leave. So you don't have a lot of opportunity for office hours unless you go to Bessemer campus. Or on Friday, notice I said Monday through Thursday, on Friday I'm on the Birmingham West campus in Dr. Pruitt's office, which is B122. That's the academic building, and this is all in the syllabus and the locator card both. And I'm there from 8 to 12 on Friday mornings. Usually I'm there a little before 8, and most of the time I'm there after 12, but officially I'm 8 to 12. Okay. So those will give you syllabus, course information, my information. Go down to the next grouping of tabs, and there's one there about third from the bottom, I think, that says handouts, PPTs, and more. PPTs are PowerPoints. Okay? And in that section, I can't remember the order, but I think the first thing I have there, I believe, is the YouTube videos. Okay? And it says PHY112 YouTube videos. What I'm doing now is recording. That's what this is indicating. I'm recording this class right now. I recorded the first class. And in the first class, I went over the syllabus. I went over my locator card. We went over safety. And we got started in Chapter 5. Okay? So, and it gave all the information about the book and stuff like that and the syllabus and other places. So you can read the syllabus if you want to, that's up here, or you can go to the YouTube video here and hear me talk about it ad nauseum. Okay, yeah, just go on and on about it. Okay, also my locator card and other stuff like that, and about the book and all sorts of things like that. Okay, in addition to the link to the YouTube videos, now by the way, let me tell you this about the videos. If you click on that link, it's going to give you a whole list of videos, except that it won't give you Okay, okay. Gives you a whole list of videos. The ones at the top are the old ones, the ones I taught this past summer. Okay? The ones at the bottom, and some of those at the top are some from previous terms as well. We didn't get as far last summer as we did other terms, so they're all from past terms. Let me put it that way. Okay? The ones at the bottom, the very one at the bottom says syllabus. That's the one that we did that time. Now you might say, well, why don't I delete the others? Well, every now and then something fails. For instance, yesterday, I think it was, on the Bessemer campus, I was teaching a class, or maybe it may have been Monday. No, it seems like it was yesterday. No, Monday. I'll decide sometime. Okay, and a thunderstorm came up, and we lost power. Once I lose power, I'm not recording anymore, okay? And so we went, so it didn't stay out very long, but if it had been out longer, I would have kept that section on Blackboard so they'd have that, even though I kept teaching and went through the section, but, you know, it came back on pretty soon, so they didn't miss a lot, okay? But, so therefore, things like that do happen. So I keep the old ones there, so you'll always have at least the approximately everything covered at some term or another. Okay. So if you want to catch up with what we did last time, and even before you came in today, it'll be on YouTube. And that link will take you right to the playlist, and then you can follow it. Now, it takes a while. For instance, right now it's probably loading my last class, okay? And when this class is over with, then I'll go to YouTube and move that to the playlist, okay? That's what I do every time. This class will probably not load within an hour or two. If I get home and have a chance to upload it at home, I'll do that. But a lot of times I'll leave it running overnight, loading, and then sometime tomorrow morning I'll get it uploaded to the playlist. So it gets uploaded to YouTube in a couple hours, but then it takes me a while to get it put into the playlist, and I can get back on. All right, any questions about how things are going? Okay. Oh, and in addition to the YouTube videos, then I have all the PowerPoints. Now, the PowerPoints for this book are pretty lousy. There's not very many of them, but I put them all out there if you want to use them to take notes on and stuff. Most of the things I'll be writing on the screen. I've got an ionizing pen. This all gets recorded. Everything I say and everything that's projected on the board. Now, my arm waving, that doesn't get recorded. So you won't have that. And I held up the book a time or two to keep from having to draw pictures. My pictures really stink. Okay. So what we were doing, we were talking about net force or total force is equal mass times acceleration. Here is how acceleration is change of velocity. Okay? Either change of speed or change of direction or a combination of the two. And velocity is change of displacement. Okay? Per unit time. When I say change, it's per unit time. All right. The question was, here's this aircraft. Full of people. Great big old airplane. Full of people. Okay? Flying along at 500 miles an hour at constant altitude. 500 miles per hour, not turning left or right, just flying in a straight line. What's the net force acting on the plane? Just make a guess. Well, there's not enough information to tell. What you think? Key here, flying along at a constant 500 miles per hour, not changing, not going up or down, or deviating left or right. It's what?
It's the same velocity.
Same velocity. Same velocity. So if it's not changing velocity, second.
Would it be the same amount?
Okay. The 500 miles an hour is the velocity and it's constant, not changing direction or altitude. So what's its question then? What's this change in velocity? 0. What's his acceleration? 0. What's his total force? 0. Because it's not accelerating. It's not changing its motion. Sure, there's tons of forces, literally, on the plane. Okay, number one, the weight of all those people is pulling it downward, but the lift of the wings are keeping it up. Okay, I'll go to that in just a second. It's hitting headwinds like crazy. If it's going 500 miles an hour, there's a lot of air resistance. But it's got its jet engines running that are exactly balancing that. So guess what? The net force is 0. The force of the air resistance trying to resist the motion is exactly balanced by the force of the engine pushing it ahead. The force pulling down, the gravity, that's exactly balanced by the lift of the plane. Now, how in the world are those wings keeping the plane up? This does not have to do with what the say is, but I'm going to tell you how that works. What would happen if I blow under this piece of paper? Any idea? What? It goes up? You're right, it goes up. Now, what happens if I blow over the top of the piece of paper? It goes up too. Whoa, what? Okay, that illustrates a principle of physics called the Bernoulli principle. What that says is that if the velocity of a fluid, now a fluid could be either a gas or a liquid, either one. The velocity of a fluid, if you increase the velocity, you decrease the pressure. Okay? And what I did when I blew, okay, there were two things happening here. When I blew underneath, I'm forcing this up, so that's why it went up. But when I blew over the top, I was increasing the velocity over the top, decreasing the pressure, so the pressure of the air underneath picked up. Now, if you ever look at an airplane wing, they're shaped like this. Big here and taper off here. Now, they do both of those things. They tilt downward, so you have air pushing up on them this way. That would be enough to keep them flying. But the other thing is that shape of the wing, the air going over the top has to go faster than the air underneath. A great deal of difference, and that gives it lift. And that's what's happening. So the lift of the plane is equaling the force of gravity down. That's why when the plane is taking off, what's it doing? Accelerating down that runway, okay? Getting faster and faster and faster, blasting those engines out the back, and when finally it gets fast enough, then the pressure over the top, the difference in the pressure is enough to lift it off the ground. That's why you have that long runway, and the plane is constantly increasing in speed. Okay? That's the airplane. Okay? You don't need to know all that, but if the net force is 0, that means it's not accelerating. If it's not accelerating, net force is 0. Okay? Now, this formula, okay, that we have here, force equal mass times acceleration, that says, now this is another terminology type thing, the force is directly proportional to the acceleration. The greater the acceleration, with a constant mass, the greater the force. The lesser the acceleration, the less the force. Or, in the other way, the less force, the less acceleration. The greater force, greater acceleration. The constant of proportionality is the mass. Now, the other way to look at this is if you had a constant force, then let's call this a constant, is equal to mass times acceleration. So let's do mass is equal to some constant divided by acceleration. That means that the mass is proportional to 1 over the acceleration. Well, what that means, when the mass increases, the acceleration decreases, if it's a constant force. If the acceleration increases, that means the mass, well, usually the mass doesn't increase, but if you had a constant force and you had an increased acceleration, you must have lost some mass somewhere. You're riding a dual tandem bike, you kicked off the person in the back, okay, and then you accelerated, okay. That's the type of thing going there. This is proportionality. This is a direct proportionality here, and this is an inverse proportionality here. And you'll run across these terms and concepts a lot later, so I thought I'd go on and do it here. Let's look at the units for force. We really should have done this with units for mass too, but there was a problem there. We have two basic systems of measurement. Does anyone know basically what they are? Systems of measurement. Basically, just about everybody in the rest of the world uses one, and here in the U.S. we use another one. Say again? Pounds, okay. I'm glad you said pounds. Pounds is a measure of force in the U.S. customary. So we have the U.S. customary system. Now, it used to be called the British system. They developed most of this. But sometime probably decades ago, Britain officially changed to the other system. Now, if you live in Britain, you probably still use some of the British system. What's the other one? Anyone know its name? Okay, we call it the metric system. Okay? There actually is an official name for it, and that is SI. That stands for System International. Why say it that way? Why don't you say international system? Well, because it was developed by the French. And the French usually put their adjective after the noun rather in front of the noun. So it's System International, or SI. Just call it the SI system. Okay? Now, unfortunately, because we live in the U.S., we have to know both systems. Okay? Now, back when I was young, if you bought an American car, a Ford, a Chevy, a Dodge, a Plymouth, any of those American-made cars, all their nuts and bolts and everything else were in fractions of inches. 5/8, 3/4, 1/2, 5/16, whatever. Okay? That everything was measured that way. If you bought, back then, when I was young, there weren't many of these, but if you did buy a Toyota or I can remember when Honda came out, so not even that, or a European car, they use metric measures. So a good mechanic had to have a set of metric measurement tools and a set of U.S. tools, based on inches, U.S. customary. Guess what? Chevrolets, Dodges, Fords, what are they built with now? SI. They don't use any U.S. customary parts anymore. Why? If you're competing in a global market, which they're trying to do, if they had our measurement, people wouldn't buy it. Because nobody carried. Nobody except in the U.S. would have both sets of tools. So therefore, they've gone. And slowly but surely, we're kind of inching toward SI. I would guess some of you work in healthcare, right? All of you? Okay. When you're measuring do the measurements on a baby, what do you usually record on the charts? Kilograms. Is that a U.S. customary? No, it isn't. That is a mass measurement. Okay? And it's SI measurement. What else do you measure? The length of the height of the child. What is that measured in? Centimeters. Is that U.S. customary? No, that's SI. So in medical, I take it you work at UAV, right?
No, I experimented with nursing school.
You what?
I experimented with nursing school.
Oh, I see. Okay. But that's what's done in most hospitals, especially the official thing. Now, what they give the parents, they'll say how many pounds and ounces and how many inches. But what they record when they're doing the things that will go into the databases, it's in kilograms and it's in centimeters, because that's SI. Everything is done, or more and more things are being done that way. Sure, the mother will be told, oh, it was 8 pounds, 3 ounces, or, you know, I don't know, 18 inches, whatever a baby would be. I don't know what they would be. Okay. So let's look at some of these measurements. Distance. What is the U.S. customary measure of distance? Foot. Okay, very good. Y'all are good. Okay. There are others, of course. You could get smaller than that, and that could be inches. You could get larger than foot. That could be yards. You could get even larger than that. That could be miles, right? And you can get all sorts of things. You could do furlongs. You could do all sorts of things, okay? What would be the measure for length in the metric system? It's almost where this term comes from. Put one letter in those first four. Meter! Okay, that's the basic unit, is a meter. And you can go bigger, and that would go up to kilometers, or bigger than that, megameter. Okay, that's a capital M with a little m. We don't usually use that one. You could use smaller, which could be your centimeters and your millimeters. And you could even get smaller than that, micrometers. Woo, that's really small. And get even smaller. You could get down to picometers, nanometers. I mean, really, really tiny. Okay? Those are the units of measure. But notice meters is in every one of them. Okay? Whereas in the U.S. customary, they're wholly different units. Okay? Now, what do these metric prefixes stand for? Anyone know? Powers of 10. Kilo is 10 to the third. Mega is 10 to the sixth. Meter is just 1. Okay? Centimeter, that's 10 to the minus 2. That's hundredths of a meter. Okay? Good way to help remember that is, what is that called? It's a penny. How much is it worth? 1 cent. Second?
1 cent.
1 cent. Cent. C-E-N-T. What does that mean? Centy means 100th of a dollar. Because there's 100 pennies in a dollar, right? So a centimeter is 100th of a meter. Okay? Just like a cent is 100th of a dollar. Okay? So that is 10 to the minus 2. I can't write with that pen. Milli is 10 to the minus 3. Duh. 10 to the minus 3, or 1,000ths. Micro is 10 to the minus 6. Nano is 10 to the minus 9. You don't need to know all these, but just say 9 and write 6. I don't know. Something's wrong with the old gray cells. They're not connecting well. Okay. 10 to the minus 9. They keep on going. Smaller and larger. Okay. You don't need to know all those. Okay. So that's length. Okay. What do we use for time in the U.S. customary system? Say again? I can't. The unit for time, the standard unit of time in the U.S. customary system. There we had time here. Is what?
Is it military time?
No, it's just seconds. If we want to go something bigger, we go to minutes. It's bigger than that, we go to hours. Yeah, you know what those are. How about SI? Time is so universal, they use seconds, okay, minutes, hours. They don't change. They still use that, okay? Now, how about velocity? What do you think we measure that with in U.S. customary system? What is velocity? or speed is change of distance over change of time, velocity change of displacement over change of time. These are your distance units or displacement units. This is your time unit, so that would be feet per second. Metric would be meters per second. Or you can use any other numerator, any other denominator. You could do that. Be fine. How about acceleration? What would that be? Change of velocity. What's velocity measured in? Either U.S. customary or metric. I don't care. SI. Say again? I just said it. Say again? Feet per second. Yeah. Feet per second. And then you're dividing again by second. So that would be technically feet per second, but the shorthand we usually do is feet per second squared. That's what we usually, you're not really squaring a second, it's just that keep from having to write it twice, you put per second squared. In in SI, it would be meters per second squared. Very good. Okay? Now, we get to force. Oh, what is the other thing here? Before we get to force, what do we need to talk about? What does that stand for? Mass. Okay? What is the what is the SI unit for mass? Anyone know? What did you measure that baby in?
Kilograms.
Kilograms. So, in the metric system, it would be gram. But gram is really, really tiny. Okay? Like maybe 2 aspirin would be maybe 1 gram. Not very much. So most of the time we do use the SI measurement would be kilogram. That's the only one of your basic measurements that has a prefix with it. Meter doesn't. Okay? That's your basic measure. Second doesn't. That's your basic measure. But mass is kilogram. Mass is measured in kilogram. The unit is kilogram. In some things you would use gram, but most of the time it's kilogram. Anyone know what it is from the U.S. customary system? Now, you've lived in that your whole life, haven't you? What is the unit for mass in the U.S. customary system? Nope, that's a force. You don't know it. I bet you don't know it. No one ever uses it. Believe it or not, it's a slug. Have you ever gone to the store and said, I'd like to buy 5 slugs of onions, please? No. They would say, what are you doing? Get out of here. We're not here to play games, you know. That is a unit of mass in the U.S. No one uses mass in the U.S. customary system. The book does. You're going to be solving problems with slug per, blah, blah, blah. But, no one uses it. No one uses it. It doesn't even have an abbreviation. If you ever use it, you have to spell it all out. You thought a slug was those slimy little things that get into your plants in the garden. No, that's a slug too, but that's not what this is. That's the unit of mass. Now, you mentioned pound. Pound is a U.S. measure for force. Pound. And by the way, what would a pound be? It would be the U.S. unit of mass, which is slugs. Yeah, we use that all the time, don't we? I'm sorry, times. I put a division sign and then I put a time sign. Slug, U.S. customary, feet per second squared. That's what a pound is. It's a slug foot per second squared. Now, in the SI units, it would be mass is in kilograms, meters, that's your distance, per second squared. Kilogram meters per second squared. They decided to give that unit a name. And they named it after the guy who did the most coming up with the concept of force. Who was that? Newton. That's exactly what it is. It's a Newton. Now notice kilogram is lowercase, Mass is M for meter is lowercase. S for second is lowercase. Pound, how they get LB out of it, I don't know, but that's lowercase. All these are lowercase. Foot is lowercase. Yards lowercase. Hours lowercase. Minutes lowercase. Feet, yards, miles, they're all lowercase. But suddenly a Newton is capitalized. Why? Named after somebody. That's exactly it. Now, back here when I put megameter, 10 to the 6th, I capitalized that one. That wasn't named after anybody. It's that we had already used the lowercase m here and here, okay? And then when we needed a micrometer, needed another m, anyone know what that little symbol is? It means micro. Anyone know where that symbol came from? In the Greek alphabet, the letter corresponding to our letter M is their letter mu. And that's the symbol for a mu. That's the lowercase symbol for a mu. So we had already used our little m, Greek's little m, so to get a megameter, we needed to use a capital M. And since megameter is a large measurement, why not use a capital letter? And everything beyond that, anyone knows what goes beyond mega? Think computers. Speed, memory. After you have kilobytes, megabytes, gigabytes, okay. And then they even are now talking about attobytes, aren't they, or something like that. It just keeps getting bigger and bigger, okay. They all go up by powers of 3. And they're all capitalized. A gigabyte is a capital G, or gigameter would be a capital G M. M is, the meter part is still lowercase, but the capital, and you go on from there. All right, enough of that. Okay, so a Newton is capitalized because it's named after somebody. It's a kilogram meter per second squared. That's your unit in the U.S. customary. I'm sorry, in SI units. In U.S. customary, it's pound. And a pound, strangely enough, is a slug foot per second squared. But no one uses slugs at all, except this book. It uses them. So let's go to example 1. This is on page 126 if you're following in your text. First of many examples we will be doing. We will spend most of our time doing examples. I had to get all that nomenclature down so you know what we're talking about. What force is necessary to produce an acceleration? So we're looking for force, and when you see the question, what force? That's the unknown. I like to label things like this. What force is necessary to produce an acceleration? There's the acceleration. That's your A of 6.00 meters per second squared. Now, is that a good unit for acceleration? Yeah, distance per time, or change of velocity per unit time, velocity meters per second, per unit time would be another per second. On a mass, and here's our mass of 5.00 kilograms. Is that a good unit for mass? Yes, in the SI system, that's what we use for mass. Now, before we go any further, this would have been covered in earlier chapters of the book. We're starting with chapter 5, so let me take time to do this. Why didn't they just put 6 and 5? Why did they put the 0.00 there?
Because we round to the 100.
Okay, you're exactly right. This is a very precise measurement. That acceleration is not just 6 meters per second squared. It's 6 meters per second squared to the nearest hundredth of a meter per second squared. Okay, that means it's good. That the device you were using didn't say 6.2 or 6.05. It says 6.00 meters per second squared. Maybe a 0.003 or a 0. It could have been a 5.997. That still would have rounded to 6.00. So the art of rounding is going to be important. This tells us this is correct to 3 decimal places. Any zero following a decimal is usually significant. Unless, of course, this was a 0 here, 0.007, only the 7 is significant there. If you got any number in front of it, then the zeros after it are significant. So this would be 5.00 kilograms. That means 5 kilograms to the nearest 10 grams. Okay, you've got a very precise measurement here. Now, are these realistic? Probably not, but they're doing this. Now, why does it matter here? When you're doing multiplications and divisions, you round to the number of significant digits. Okay? When you're doing adding or subtracting, you go to the most precise or the least precise, and that's what you go to. We're not going to be doing that many addition, subtraction. We will be doing lots of multiplication and division. So what's the formula for your force? We had it a short time ago. What was it? Times acceleration. So we plug those in. The mass is 5.00 kilograms times the acceleration is 6.00 meters per second squared. And when you multiply those two together, what do you get? 30.0. Only 3 significant digits. Don't put that other 0 out there. That would give you 4 significant digits. You can only have 3, so it's 30.00. And then you multiply the units as well. That could be written as a kilogram meter per second squared. But what is a kilogram meter per second squared? Named after? Newton. That's a Newton. 30.0 newtons. That would be the force, the total force and net force that would be required to produce an acceleration of 6 meters per second squared on an object that have mass of 5 kilograms. Okay? Make sense? Okay. Now, next example is a lot like it. What force is necessary to produce an acceleration of 2 points? Okay, again, I should have done this first. When I read that, what force, I write down force is my unknown. That's the question, what force? Okay, is necessary to produce an acceleration of 2.00 feet per second squared. Is that a good unit for acceleration? Yes, distance per time per time. That's we get acceleration. On a mass of, guess what they're going to use? 3.00 slugs. The only place you'll ever see this used is this book, just about. Okay? 3.00 slugs. So, what is force? What's your formula? Okay, it's mass times acceleration, and that would be 3.00 slugs, no one ever uses that, times 2.00 feet per second squared. And what does that give you? 6.00 newtons is SI. What is U.S. customary for force? Someone gave it to me earlier. Say again? Pounds, you got it. Where the LB comes from, it's Latin or something like that, but 6.00 pounds.
So if you use slugs, it's going to be pounds, and if you use kilograms, it's going to be newtons.
Yeah. If your mass is in slugs, if you're using U.S. customary units, which is slugs, feet, seconds, that kind of stuff, you're going to come out in pounds. If you're using SI units, which would be meters, kilograms, seconds, that kind of stuff, you're going to come out in newtons. You're absolutely right. All right. Now, this is probably discussed in earlier chapters, and since we didn't do the earlier chapters, let me take a few moments to give you a few hints here. Here is a formula, force equal mass times acceleration. That's Newton's second law formula, right? You can come up with two other equations based on that one. Anyone know how to do that? How? Okay. Here, you could divide both sides of the equation by, pick one of those. I don't care which. Second? By acceleration. Okay. Now we have the accelerations go out, and you have mass is equal to force per unit acceleration. Or you could have gone back to that first one, force equal mass times acceleration, and divided by mass. And then the masses go out, and then you have acceleration is equal to force per unit mass. Okay? So anytime you have a multiplication or a division type formula or equation, you can change it usually to two or three other equations that are also useful. Now, when I was in the Navy school system is probably not known as the best in the world or anything else like that, but it certainly was pretty good. But they did this in just about every class I had. They showed these little mnemonic devices that help you. And you can use either a triangle or a circle. I really don't care which. I kind of like myself triangles a little better, but you can use either one of them. And when you have a formula like this, which is force is equal to mass times acceleration. Now notice here, these both shapes here have a horizontal line and a vertical line. The vertical line is a multiplication line. Horizontal line always means division. Whatever's on top is divided by what's on the bottom, right? So that's your horizontal line is a division line, vertical line is multiplication. That's why I put a multiplication symbol. So the thing that stands by itself with multiplication here, put the force up here, the mass times acceleration down here. Or over here, same deal, it's just a circle rather than a triangle. Force is mass times acceleration. So if you know one of these, you know all of them. Because what you do, if you're looking for mass, cover the mass, and mass is equal force divided by acceleration. Or if you're looking for acceleration, cover the acceleration, you get force divided by mass. So every test I ever saw them give in a Navy class, the first thing when people got the paper, they immediately wrote down whatever formula they were using that they used this, and they put down these triangles or circles and put them in so they could always know exactly what way to use the formula. Now the reason I said that is the next example. Can I erase what's here? Okay. All right. Example 3 says, find the acceleration. So there's the unknown here. Find the acceleration produced by a force, the force of 500 newtons. All right. Time out. Notice in the book, they put a bar over that second zero. What does that tell us? That tells you that zero is significant. So if you have a significant digit here and a significant digit there, everything in between has got to be significant. So this is good to 3 significant digits. Okay? That's what the bar means. Okay? And already what units are we dealing with? Say again? Okay, yeah, that's the unit, but what system of measurements? SI. We're dealing with SI. Good. Applied to a mass of 20.0 kilograms. That also reinforces we're dealing with SI units. 3 significant digits, and what would acceleration be? Anyone remember? If not, you can do your little triangle or circle or however you want to do it. That would be force divided by mass. You got it. Now, I'm going to write the force, 500. I'll put even the bar over it. I really don't need to. But rather than writing newtons, what is a newton? The basic units. Kilogram, meter per second squared. Divide that by the mass is what? 20.0. What unit? Kilograms. Hey, don't ignore your units. Units are your friends. If you keep up with them, use them properly, they'll let you know whether you got the problem in the right order or not. Because looky here. Here you have kilogram up here. That cancels kilograms there. And you're left with meters per second squared. That's a great unit for acceleration, isn't it? So units are your friends. Don't ignore them. Don't mistreat them. Be kind to them. They're your friends. Okay, now I've got to divide 20 into 500. I'm not really worried about significant digits at this point. So all I'm going to do, I'm going to divide both of those by 10. Okay? Dividing, missing a 0. Then 2 will go into 5 twice with 1 left over. 2 will go into 10 5 times, and that's where our decimal goes. So I'll need one more 0 to make 3 significant digits, and that will be meters per second squared. Did I do that right? That is an incredibly large acceleration. That means you're increasing speed 25 meters a second every second. You're not going to sustain that acceleration for more than a second or two. It just is not possible. But this is just a made-up problem anyway. So that is the correct answer, 25 meters per second squared. Now, the book does it in 2 steps and does your conversion to acceleration units. That's fine. If you like doing it that way, you can. I just say, what is a Newton? It's a kilogram meter per second squared. All right, we finished 5.2. Okay? Now, 5.2, unlike 5.1, has some problems with it. Now, your back of the book has answers to odd number problems. So what I do is assign you, and I'll let you choose which ones you want to do some of the odd number problems 1 through 7. They just give you masses and accelerations. You're asked to calculate forces. Then do some of the odds, 9 through 15. There they give you masses and forces and ask you to calculate accelerations. Then you choose some of the others, any of the other odds, 17 through 33, any of those, and work those out as well. Okay. You decide how many you need to work till you feel confident. I understand this. Then go on to some others. Say again? Okay. The answers are in the back. If you can't get the answer, try to figure out how to get the answer. If you can't, don't get frustrated. Bring that problem to class next time. I'll always ask at the beginning, are there any questions? It's a good time to ask. I couldn't get number 23 to work. How do we do that? We'll work number 23. Okay? Now, remember when we were talking about tests? What kind of test did y'all want to have? Take-home. Oh, that's right. You did, didn't you? Okay. Now, since you requested take-home test, remember I told you that I'll always give you at least 2 class periods to do it. 1 class period to ask questions, the next class period turn it in. So I always give you at least 2 weeks to work on your test. Now, if you finish it sooner, you can. Now, remember I told you what are some of the legitimate questions you can ask. I don't understand what this problem was asking for. What do you mean by this? That kind of thing. Okay? A illegitimate question would be, can you work number 7? My answer will be yes. And that's all. I can work number 7. I gave you the problem. But will I work number 7? No, that's a test question. You're going to be graded on that. But guess what question I will work? Anything from the book. So if you find a test question, when I give you your first test or any subsequent test, and you have no clue of how that worked out problem, Find one like it in the text. Find one like it in the text. See if you can work that one. The answer's in the back of the book for it. If you can't figure out how, bring that question to me. Can you work number 23 on the problem set? Sure, we'll try. So we'll work it. That will then give you, I hope, a good lead on how to work the one on the test. So you can always do that. All right. Any questions on 5.1 or 2? Okay. Let's move on to 5.3. Now, notice we only did Newton's first law and second law. We're later going to get around to the third law, but before we do, here's an issue that comes up. And it's sort of a strange way they phrase it. It's weight, gravity, and weight. Okay? Now, I kind of don't like the fact they just say weight. Just say gravity. And I'll tell you why in a minute. Let me first give you the definition. The weight of an object, I abbreviate like crazy, is the amount of gravitational pull exerted on an object by the earth, or by whatever big body you happen to be standing on. I'll put the earth. Because most of us, most of our lives, for me, my entire life, I've lived on the surface of the earth, okay? I haven't gone to any other planet or moon or anywhere else, so I've spent my whole life on the earth. And I imagine most of y'all have too, and probably will, okay? So, we'll just leave it on the earth. Now, I want you to focus on one word here. Gravitational pull. What was a push or a pull? A force, exactly. Weight is a force. So guess what units it will have? Either what are the 2 units for force? We were just talking about it. Say again? I can't hear. No, wait. No, mass is not force. That's a mass. What are the 2 units of force? We just did problems with them. Pounds are named after newtons, of course. Those are your 2 units of force. So weight is a force. It's going to be measured. And when on Monday mornings, I get up, if I can remember to do it, and before I get into the shower, I stand on the scales to see weight, and it's how many pounds. Weight is a force. How much gravity is pulling down on me. I wish I could cut down on gravity some because it's pulling way too much, okay? But I can't. If you want to know a really good weight loss program, go to the moon. Because you're going to lose weight. You're not going to lose any mass, but you'll lose weight because the moon has a much smaller gravitational pull than the Earth does. So there, good way to lose weight. Go to the moon. Of course, when you come back to Earth, you weigh the same thing. Okay, no. It's not a permanent. It's just your gravitational pull. Okay. So, weight is a force. Weight is equivalent to force. So, your units of weight would be pounds or newtons. Okay. Now, if that force is not balanced by other forces, for instance, when I stand here, gravity is pulling down on me with an enormous force, but the floor is pushing up on me. So I balance. I'm not sinking into the floor, thank goodness, nor am I flying off the floor. Yeah, that sense of that, right? So neither of those is happening, so I'm met with a balanced force there. So weight is usually not your net force or your total force. It's usually one of your component forces. Like that airplane flying, its weight was whatever the gravity was pulling down, but the lift was pulling against it, so it had a zero net force. So weight is most of the time not a total force or net force. All right. Now, they do show a pretty good illustration here. If I were holding a brick here, okay, the weight of that brick is the force gravity is pulling down on it. If I'm holding it, I'm exerting friction on it, keeping it from falling. But the minute I release it, now the net force on the brick is the thing because I'm not holding up on it anymore. So now the net force is gravity pulling down the weight of the brick. So it can be your net or total force, but if there's no motion, it usually is not. So, since weight is a force, we can call that, and this book calls it F sub W. That's a force, but it's the force due to weight. Okay? And it's equal to the mass of the object times the acceleration due to gravity. Now, I kind of hate that they just say gravity. Gravity is represented by an acceleration. They should say the acceleration due to gravity. Okay? Now, since we spend most of our lives, in fact, all of mine, on the surface of the earth, we need to know what the acceleration due to gravity is on the earth. And here are the numbers. Acceleration due to gravity on the earth in, which you want first, SI or US customary? I don't care. SI. That would be 9.80 meters per second squared. Remember, it's an acceleration, meters per second squared. In US customary, that would be 32.2, I'm pretty sure it is. Yeah, 32.2 feet per second squared. Again, it's an acceleration, so it has acceleration units. Distance per time per time. Distance per time squared. Now, that's what we use to measure weight. Weight is a type of force. When you have the force up here like we did in this problem, that was the total force or the net force. This one is the force due to weight. Okay? A lot of other books would just use little w to represent that. This book uses F sub w. Okay? Now, ready for another example. Find the weight. What do we represent weight with? F sub w. So that's the unknown. That's the find the weight of 5.00 kilograms. Yeah. What is that a measure of? They didn't tell you. What does kilogram measure? Mass, yes, exactly. That's the mass. So, how do we find the weight? What's the formula? Is what? Right there. Well, I can't hear. My hearing's really bad, people. Mass times acceleration due to gravity. Okay? So that would be mass times acceleration due to gravity. What is the mass? 5.00 kilogram. And what acceleration due to gravity do we use? 9.80, because we're in SI units. 9.80 meters per second squared. Notice they give it to us at 3 significant digits so we can do our calculations. Now this one you might need to pull out your calculator, or maybe not. Anyone know what this comes out to be? Second? Yeah, multiply. Anyone say? I can't hear. 49 point, 0, what unit? Second? I can't hear. N, newtons, okay, capital N newtons, exactly. The force, the weight is measured in newtons, okay? And what the book get? Oh, look at this, they got it right, good for them. Okay? All right, I'm running out of room, can I erase these? Anyone need it a little longer? This is example 1, about the middle of page 129. All right, to erase? Okay. Okay, speak up if you can't, because I don't hear well. Okay, so I'm going to erase. And the example 2 says, find the weight. What symbol do we use for weight? F sub W. That's your unknown here. Find the weight, okay, of 12 slugs. 12.0 slugs. What is that a measure of? That's your mass. In what units? What system of units? U.S. customary. So what's the formula for weight? You gave it to me before. Say again? That's the symbol for it. What's the formula for it?
Mass times gravity.
Acceleration due to gravity. Perfect. And what was your mass? 12.0 slugs times what acceleration due to? 32.2. What units? Feet per second squared. Okay, that one, I might need a calculator for that one. It's going to make my head hurt to try to do it. It'd be 64.4 and then 320, that would be 386. Is that what you said?
Yes, sir.
What unit?
Pound.
Pounds, you're right. Slug foot per second squared is a pound. Did it come up to that exactly? Or are you just reading from the book? It did. Okay. Oh, you did a calculator. Perfect. 3 significant digits, you got them right there. 386 pounds. Huh?
386.4 petroleum.
Aha! Okay. I wanted to hear that. Okay. Actually, this came out to be 386.4 pounds. But that's 4 significant digits. We only have 3 coming in on both of those, so we can't have 4 significant digits coming out. You know the old computer programming slogan they used to use? Garbage in, garbage out? Well, same thing with units. If you only have 3 significant digits coming out, there's no way you can have 4 coming in. You can have 4 digits coming out. So you round this. How do you round? You had 3 digits, so you count 3 digits. 1, 2, 3. Look to the right. If that number is less than 5, delete it. If it's 5 or more, bump up the previous one. So that, if it would have been 0.6, you'd have been 387 pounds. With that being a 0.4, just drop the 0.4, 386 pounds. That's how we do normal rounding. Okay. And that's what the book got. Good for them. All right. Now, I've already given one illustration of this, but now I'll give another one. And somehow I get my pen all tangled up in all the wires here. I don't know how I do that, but I do. Okay. I think I'm going to go and erase these. Is that okay? Everybody got it? Okay. Weight versus normal force. Now, I already gave this, I didn't give the name to it. If I'm standing here on the floor, certainly the earth is pulling down on me with the acceleration due to gravity, and that gives me my weight, which I'm not about to tell you, okay? Okay? But I'm not, thank goodness, crashing through the floor. That's because the floor is pushing up with me, on me, with an equal but opposite force. That's called the normal force. Normal because it's perpendicular to the force. That's what normal means in physics and math sometimes, is perpendicular. So that's the normal force. Now, if I were to get up here, I'm not going to, and stand on this table, hopefully it would hold me, and then the normal force of the table would be pushing up me. Especially if I stood over here, I think it would have a real good shot. If I stood in the middle here, I might start bending that a little bit. But hopefully it wouldn't crash. But if I were to put, y'all know what if I say a 1 by 10, what I mean by that? Board. 10 inches wide, 1 inch thick. If I put a 1 by 10 board across here, and then climbed up on the chair and on the table and then stepped onto the board, what would that board do? Say again? Oh, yeah, I was afraid you said that. It would bend, wouldn't it? She has me snapping it. Probably. Okay. No, you're right. It probably would break. But before it did, it would sag and then probably break. Okay? Because its normal force isn't strong enough to support my little bit of weight. Okay? Depending. Okay? It would probably break. Because the normal force is not strong enough to counteract my weight. So that's what they mean by weight versus the normal force. And this is where that next slide, remember way back then I said there was another slide coming up? This shows that. Okay? Here is that brick that I was holding before. Now I put it on the table. Okay? And the gravity is still pulling down with a significant force on that brick. But if the table's strong enough, it's pushing up on the brick with an equal and opposite normal force. Now again, if that table was not strong enough, was like that 1 by 10 or something like that, it may sag a bit and now the tensile force is holding up. Or if it's really lousy, like if it's a piece of paper, if I ran paper from here to there and put a brick in it, no, it's not going to have enough normal force to hold up. So then it would break. So if the normal force is equal or greater than the weight, then it will support the brick. So that's what we mean by a normal force. It's a force pushing up, usually against the force due to gravity. It's perpendicular. F sub n, normal force, is perpendicular to the contact surface. Okay? Now, that's all they do. They don't give you any problems with that. Let's see what the next one's going to be. Whoa. Well, that's the next page. So we may get there tonight, but yeah, we got about 12 minutes. So we'll see if we get there. Let's look at the concept of mass versus weight. We've already done that. Okay? Now, any of you go to the grocery store and buy something you put on the scales, okay? You know, like produce or something like that you're buying, usually by the pound. But those scales usually have 2 sets of numbers on them. What are the numbers? Outer numbers are usually pounds, but the inner numbers are kilograms. Now, we don't pay any attention to the kilograms. But what's wrong with that picture? Pounds is a measure of, what have we been talking about? Yeah, that's what unit, but what's the measure of? Weight. Whereas kilogram is a measure of mass. They shouldn't be comparing those two. That's apples and oranges, or mushrooms and no. Okay, all right. So, why can we get away with that? Because we're on the surface of the earth. The only difference between weight and mass is not a difference per se. It's a constant number, a multiplier. 9.80, or 32.2. It's just a constant number, so you can just scale them to different things. But you really should be comparing pounds to newtons, not pounds to kilograms. But no one in the grocery store measures anything in newtons. They measure things either in pounds or kilograms. If you go outside the U.S., you'll not see pounds on many cans. It'll be how many kilograms, how much mass there is of that, not what the weight is. Okay? So that's what they're talking, weight versus mass. Okay? Note that the mass of an object remains the same, but its weight varies according to the gravitational pull. And this is what I was making a joke about. If you want a good weight loss program, go to the moon. Okay? You're going to lose weight. Not going to lose any mass, but you will lose weight. Okay? Because, I've got to go back to my pen. Okay? What was that formula for weight? You tell me. F sub W is equal to mass times the acceleration due to gravity. And guess what? You go to another celestial body, like the moon, that acceleration due to gravity is going to be very different. The moon is about 1/6 the gravitational acceleration the Earth has. So you're going to lose 1/6 of your weight. Will you change any mass? No. Okay? You come back to Earth, multiply it by 6, you're back the same weight you were before. But you lost weight when you were on the moon because that was a function of your gravitational your acceleration due to gravity. So let's say that an astronaut has a mass of 75 kilograms. So the mass of the astronaut is 75.0 kilograms. Okay? What's its weight on Earth? We don't know whether that's a male or a female. They have them both. I think it's probably a female, but I'm not sure. What's the weight? F sub W is equal to 75.0 kilograms times second.
1.63.
Okay, we're talking about on Earth.
Oh, on Earth.
Yeah.
9.8.
9.80. What units? What units? I hear mumble, mumble, mumble. What units?
Is it mass over second squared?
Not mass. Meters per second squared. Distance over time over time. Meters per second squared. And do that, and what do you get? Give me all the digits you get. It's going to be something on the order of 740 something.
735.
735. Is that exact?
Yes, sir.
735. What unit?
735.
735. I'm sorry. I heard it right, but I wrote it wrong. Okay. 735. What unit? Help me, somebody. Newtons, exactly. 735 newtons on Earth. But if that astronaut lands on the moon, where the acceleration due to gravity is less than that is on Earth, the astronaut will still have the same mass. Unless they threw up going up. No, we won't go into that. Okay? Still has the same mass, but because the acceleration due to gravity is less, it will have less weight. Okay? So it says find the 75.0 kilogram astronaut's weight on the moon, where G on the moon is what you were reading out earlier, 1.63 meters per second squared. So what is the weight of the astronaut on the moon? What's his mass? 75.0 kilogram times, what's the acceleration due to gravity on the moon? 1.63 meters per second squared. And what would that be? Give me all the digits, huh? 122, you said?
Yes, sir.
122.25, what units? Newtons. But that's too many digits. So what do? We count 1, 2, 3. That's all we had, 3 significant digits. Look to the right. That's less than 4. So that'll be approximately 122 newtons. Boy, what a weight loss program, huh? It went from 735 newtons down to 122 just by going to the moon. Doesn't mean they lost mass, they lost weight, because weight is a function of the gravitational field in which you live. All right, then there's one other, and this one I don't find very confusing at all, but they do make a point of it. They say mass versus volume. Okay, mass is how much of an object there is. Volume is how much space it takes up. Okay? That's a very different thing. Mass is measured in what units? U.S. customary or SI? I don't care. Kilograms in which one? SI or? What would be the other unit? One we never use. Slugs. And slug would be in U.S. customary. Whereas volume, now there's several ways to measure volume. Most of the time in SI units, we use cubic meters because it's length times width times height. That's how much space it takes up. Okay? In U.S. customary, we would use cubic feet. Okay? But there's other ways to measure volume. You could use, if it's liquids, you could use gallons or quarts. Whoops, wrong place. Sorry, don't write it. In U.S. customary, we could use gallons or quarts or pints, other things like that. In the SI units, we could use something like liters, okay? Or if you're doing medical dosage, what would you have? Milliliters, right? Or in the old days, they used cubic centimeters, which in the old days they called cc's. Anyone ever heard them called cc's? Yeah. Some people still do that. Okay, those are metric units for volume. Most of the time we'll use cubic meters or cubic feet. Very different from mass, which is in kilograms or slugs. Mass measures how much of an object is there. Volume measures what space it takes up. Very, very different things. All right. Problem 5.3. I would do either 1 or 3 or both. They're both in the back of the book. Either any of the odds 5 through 9. They should all have answers in the back of the book. And then I would do sum of, say 11, or I would do 11, either 13 or 15. And then just any of the other odd ones, 17 to 29. Okay? Good deal. All right. Let's at least introduce what's coming next. And that's 5.4, which is friction. Okay? Now, y'all have a general idea what friction is? Would you say friction's good, bad, or indifferent? What you think? That guy pushing that crate across the driveway, was he thinking friction was good, bad, or indifferent? Bad. He was having to push really hard to overcome that force due to friction. Any of you drive here today? Was friction good, bad, or indifferent? I'd say, well, okay, indifferent may be good. The tires on the road, good to have friction there. Otherwise, you're sitting right where you were, spinning around. If there's no friction, you're not moving. But in your engine, if you had a lot of friction, your engine's going to overheat and probably freeze up, and it would be a bad thing in your engine. So, yeah, maybe driving over it would be somewhat indifferent. Well, what is friction? I think I'll go on and write it here. Friction, whoops, let me get my pen back. Black. Okay. Friction is a force. There we have another force, folks. Friction is a force, okay, that resists the relative motion of two objects. Caused by irregularities in the surfaces. Okay, I put surfaces. They said surfaces. Either sliding or rolling across each other, which tend to catch blah, blah, blah. It goes on and on and on. Okay? And that's what this picture is showing. Here we have a front-end loader or something like this pushing on that thing. That guy couldn't move it. So he's pushing on that. The motion is this way. Friction always, always, always opposes the motion. If you were pulling on this, friction would be this way, always opposing the motion. Okay? Why does it oppose the motion? Because if you got a microscope or something else, look down here, you would see this box probably is a little rough on the bottom. Has some irregularities in it. This surface down here is probably almost definitely somewhat rough. Now, this shows a place where it might be not too hard to move. But if you can imagine this groove from the top thing falling down into this indentation on the surface here, that's going to be hard to move. Because when you're trying to pull it this way, this thing's pushing against the wall here, that's the wall pushing against here. If this was down in here, yeah, that would be really hard to move. That's what friction is. It's something, a force that always resists the motion. Okay? And we'll talk about more specifics on this next time, because I think we're just about out of time tonight. All right, so let's see. I think we got that page covered. We'll start at the top of the next page. We'll talk about two types of friction. We'll go over there. All right, good deal. All right, we'll see you next week. I'd say work on those exercises because it's not going to be too long before we have our first test. In fact, let's see. I think I'll be giving it to you next time. Okay. All right. Good deal.
This video will be uploaded by tomorrow.
What's that?
You said this video will be uploaded by tomorrow.
Yeah, sometime tomorrow. It'll probably be, see, I have a 8:30 class in the morning, so probably sometime after 10 or so. Sometime there I'll try to get it uploaded. Yeah, good deal.
Thank you very much.
All right, have a good... Oh, and by the way, I meant to tell you all this. There was a good news, bad news situation. The bad news is that next Monday's a holiday, Labor Day, so there's no school. But the good news is it doesn't affect us any. We meet on Wednesday. Yes, all right, good deal. I got that recorded if anyone listens. Okay.